This is Lab 3, the magnetic field of a bar magnet by me, Zach Uhlig. So just a little bit about the purpose and background. The purpose is to measure the distance dependence of the magnetic field due to a small bar magnet, and then compare the measured value using the magnetometer to the computational value in GlowScript. So the intro to Biot-Savart law, the big idea is that moving point charge / flow of electron creates a magnetic field, and the Biot-Savart equation is below, where mu naught over 4 pi is a constant, QV cross R hat, where R hat is opposite location to source location, R squared is the distance, Q is the charge, and V is the speed of the charges. And so extended version of the Biot-Savart law is that loops of current are actually magnetic dipoles, and they're analogous to electric charge dipoles. And when Z is much, much greater than R, the magnitude of the magnetic field of a ring looks like this, where I pi r squared is equal to mu, which is equal to current times the area. And so for a bar magnet, it's the same thing, where you have mu equal to the magnitude of the current times the area, and mu naught. And it differs when it's on axis and perp axis by a factor of 2 for when it's on axis. And so we have to account for the Earth's magnetic field because it has its own magnetic field, and we have to take this into account for the calculations with regard to the bar magnet because the app has no way to differentiate between the magnetic fields. So our experiment, defining the system and the surroundings, where the system is our phone and the magnetometer, and the surroundings are the bar mag B field, the Earth B field, and everything else. And it's important to note we cannot ignore Earth's magnetic field. And so the main results of the equation are illustrated here with the arrows pointing on axis and in the perp axis and all of the observation data that we collected. And so just a little bit about the experiment setup. We have the bar magnet perpendicular to the magnetic field of Earth, and then we have to find both the perp and the on-axis distance where the x component was 0 and the y component 0 respectively, and put it in the top right corner of that. And so for taking measurements for the distance dependence, we found that the magnitude of B bar is equal to K R to the N, where K is a combination of parameters and constants, and by measuring B bar, we'll be able to determine N, and we can see measuring distance at different magnitude of B bar, there's a clear drop off. And so more measurements for the perp and off axis. These are listed below, and then we have the BY corrected and BZ corrected because of the magnetic field due to the Earth. And so our overall observations are listed here. You can pause it if you'd like to read through those. And then so for finding N in B bar, we have our equation with natural log of Bx versus the natural log of R, where we use our slope in terms to do N, where N ends up being around 0, or it should be pretty close to 0. So then we're able to calculate mu based on the magnitude of B field on axis, where we get 2.985 ampere meters squared. And so this is the overall summary of our data if you'd like to pause it. And then onto the computational model. So we have the constant and the function, the dipole function, with R mag, R hat, and B using the equation below. And then we also have our on-axis and perp axis for creating the arrows and the vectors. And then this is the code for creating the 45-degree arrow. And this is our model where we have the axis 1, 2, 4 perps, the distance D, and the purple arrow, which is B at 45 degrees at a distance D. And so just a number of the differences, the measured B net versus the computational measured as 4.89 e to the negative 5th Teslas, where the observed was 9.45 e to the negative 6th Tesla. So these values are close-ish, but variability is going to be expected with experimentation, whereas computational modeling has little room for error. And then for the question 1, what if? So if we didn't account for the Earth, all of the results gathered would vary by a constant x, meaning the x components for the observed calculations would all have been off by the same amount, and this would have led to the net magnetic field differing by some value. And for question 2, if you stuck 2 bar magnets together and reran the experiment, the net electric field would be increased by some scalar value, as the B field should be stronger with 2 magnets, because the mu would be larger. And then overall conclusions, the Earth's magnetic field plays a role in calculations larger than one would expect, and the magnetometer, as it gets closer to the magnet, results in an increase in the x component. And a number of errors could have been the phone setup could have been off, and the magnet may have not been perfectly perpendicular. And what I found really interesting is you can model the bar magnet both on and off axis using the same equation computationally. Thank you.